In this video, we're going to go over some applications of Newton's second law. So, as you can see here, I've got an incline, we've got a mass on the incline. Now the weight of the mass, mg, of course, acts straight down, like so. And that weight can be resolved into two components because it is force. One component perpendicular to the surface. Now that's the normal. Remember we said that the normal force is always perpendicular to the surface. And then this component over here, which is the x component if you sort of tilt the axes around, that's the component that tends to accelerate the box down the incline. So the x component is computed by mg sine theta, and then this is the force, as we said, that accelerates the mass down the incline. And then the y component, right here, wy, that's mg cosine theta, and that's the normal force. So here is a problem that's an application of what we just said. We've got a 60 kilogram skier on a 25-degree slope. We want to know what her acceleration is, if friction is negligible, and B, if friction is known to be 45 newtons. So the first part is regarding friction. First thing we need to do is to determine Wx, because that's the force tending to accelerate her down the incline. So that's mg sine 25 degrees, and if you work through those values, that comes out to be 248 newtons. And so now her acceleration is that force divided by her mass, which is 4.13 meters per second squared. Okay, now if friction is present, then that frictional force opposes the motion, so we're going to subtract that from the force tending to accelerate her down the incline, that 248 newtons. So that gives us 203 newtons. So her acceleration is that force, that net force, 203 newtons, divided by, again, her mass, 60 kilograms, which is now 3.38 meters per second squared. So you can see that her acceleration is less when friction is taken into account. All right, another application of Newton's second law is tension. And tension is the force along a flexible medium, such as a rope or a cable. So right here, we've got a mass here, and assume this arrow here is a rope, so there's tension along there. And of course, the weight acts downward. So assuming this is at rest, then the tension on this cable or rope is going to be equal to the weight of the mass. So that's 2 kilograms times 9.8, or 19.6 newtons. So here's another example of an application of tension. Suppose instead of this box being at rest, like it was in the last slide, it's accelerating upward at 2 meters per second squared. Okay, so if that's the case, then we know that the tension has to be greater than the weight. That's why it's accelerating upward. So we can say that the net force is equal to T minus W. We're saying T minus W because, again, we know that the tension is bigger than the weight. So if we want to find the tension, then we just say the tension is equal to the net force plus the weight. Well, the net force is going to be ma, so that's the mass of the box, times its net upward acceleration, which is 2 meters per second squared, plus the weight, which is 2 kilograms times 9.8, or 23.6 newtons. Another quantity that we talked about a little bit, but haven't gone into too much detail, is friction. So friction is a force, and it always opposes the motion. So if the object is moving to the right, friction is acting to the left. The object's moving to the left, friction is acting to the right. Two kinds of friction. There is static friction and kinetic friction. Static friction is encountered by a body that is at rest. So in other words, if there's a body and you want to get an object moving, you've got to overcome its static friction if it's at rest. On the other hand, kinetic friction is friction encountered while the body is moving. So if you get this object moving and you want to keep it moving, you've got to apply a force equal to the kinetic friction. Now, almost always, the static friction is greater than the kinetic friction. So in general, it's harder to get an object moving than it is to keep it moving. Okay, now, to compute friction, static friction is equal to something that's called the coefficient of static friction times the normal force. Now, this coefficient of static friction depends upon the nature of the surface. So typically this is something that you're going to look up on a table, and it depends upon the nature of the two surfaces. Is it wood on wood? Is it metal on wood? Is it rubber on asphalt? So on. Okay, kinetic friction, almost the same, only in this case it's the coefficient of kinetic friction times the normal. So now, the normal force, remember, is oftentimes the weight, although not always. If you're on a horizontal surface, then the normal force is equal to the weight. But like we saw on the previous slide, the normal force on an incline was the y component of the weight. Okay, well, more on that in the next slide. But notice that mu here is a unitless quantity. So if you took either one of these equations and solve it for mu sub k, it's going to be force and kinetic friction divided by the normal. Both of those quantities have units of newtons, and so that'll cancel out. Okay, so a quick example here. We want to compute the force needed to get a 5 kilogram wood box moving on a wood surface from rest. And then B, the force needed to keep it, same 5 kilogram box, moving also on a wood surface. So to get it moving, we're going to take the coefficient of static friction for wood on wood, and I looked that up on the table, and that's 0.5, times the normal force. This is a horizontal surface, so it's just going to be the weight, 5 kilograms times 9.8. So the force due to static friction that we'd have to overcome is 25 newtons. On the other hand, to keep it moving, almost the same calculation. The only thing that's different is now we're going to use the coefficient of kinetic friction, which is 0.3, and multiply that by mg, and that comes out to be 15 newtons. All right, so another problem we can do, this is similar to the one we did earlier, but we want to calculate the acceleration of a box down an incline. Again, the angle is 25 degrees, but this time we know just the coefficient of kinetic friction as 0.4. Notice we don't know the mass of the box. Okay, so the first thing we want to do is to compute the x and y components of the weight because it's on an incline. So the x component, mg sine 25, is 4.1 meters per second squared times m. Remember, this is the force that tends to accelerate the box down the incline. Wy is mg cosine 25 degrees. That's m times 9.8 times 0.91, or 8.9 meters per second squared times m. Remember that Wy here is the normal force. Okay, so now we can say that the net force on the box, the sum of the forces, is equal to the force tending to accelerate it down the incline, which is Wx, minus the force due to friction, or Wx minus mu times n. Okay, so the net force is Ma equals Wx, 4.1 meters per second squared, times m, minus the force due to friction, which is the coefficient of friction, that's mu, that's the 0.4, times n, and remember, is the y component of the weight, which is 8.9 meters per second squared times m. Now notice we have an m term here, here, and here. So we can divide both sides of the equation by m, and m will cancel out. And so now we just have the acceleration is equal to 4.1 meters per second squared minus 3.6 meters per second squared, or 0.5 meters per second squared. So this acceleration is independent of the mass. It doesn't matter what that mass is.